Okay, so this is what I'm going to be talking about. So seeing with spikes, going all the way from motion detection to object recognition. So this work is done with one of my former students, Garrick Orchard, who's now at National University of Singapore. So let's start with the motivation and background a little bit. So, we've seen a lot of this, so I will not belabor it. So here are some comparisons between different machines out there. So on your left, there's the most powerful supercomputer in the world, so it's about 33.9 petaflops. The most efficient one is something around 2.3 petaflops. The brain, something on that order, anywhere from 10 to the minus 3 to about 10 petaflop. If you think about how many gigaflops it does per watt, so the biggest one is about 1.9. The most efficient one is about 4.5, whereas this is where we win, right? So we win because we do about 500 to 10 to the 5th gigaflops per watt approximately. And recently, you guys may remember Watson, IBM Watson playing Jeopardy against Jennings, and Watson won. I'm not impressed by the fact that Watson won, and the reason I'm not is because of the following. Watson basically was approximately 1,500 humans with identical memory of the entire internet. I mean, I think, that 1,500 humans that way, with that kind of memory, will beat one. I agree completely. But nonetheless, the human brain is something that is obviously impressive in its computational powers, in efficiency, in its size, in its weight. So that is why we are interested in trying to see what we can do by mimicking some of the computation that it does. So a moment ago, we heard Steve give a brilliant talk about, some of really highbrow personage in the computation. He talked about Ada. He talked about Lord Byron and Alan Turing. I'm going to bring you a little bit more down to earth and talk about Tupac and Biggie. And I'm pretty sure that you haven't seen a technical talk with Tupac and Biggie being mentioned. So the reason I put their pictures up because there was this famous war that happened between them, where East Coast and West Coast rap style were being litigated, for lack of a better word. And that similar kind of thing happened in the late 80s, early 90s between the East Coast and the West Coast flavor of neuromorphic engineering. So the question was to spike or not to spike. And the interesting thing about Tupac and Biggie is that despite the fact that there was this animosity that was being portrayed through the press, in the back they were actually friends, and they were working out some of their differences, but they were portraying this thing up front. So here is the equivalent of the Tupac and Biggie. On the West Coast there was Carver Mead, presenting his version of what neuromorphic engineering is, and folks like John Lazaro and Michel Mohawald, who many of you may know. But on the East Coast, there was Paul Mueller and Jan van der Spiegel, who I worked with. And then we had also Andreas Andreu, who was at Johns Hopkins, but he had been bitten by the West Coast bug, so I called him a left coastie. And Kwabena Bohan at that time was working with him. And then eventually Kwabena ended up going to work with Carver Mead. So this fight or this debate that was going on was a question of trying to figure out what is the right way to represent computation that are more brain-like, right? So the West Coast perspective was basically always go sub-threshold in the computation of the transistors, because that is more representative of the ion channels in biology. We on the East Coast cared more about how can we do things fast, how can we do things taking advantage of what we know we can do very well above threshold. But out of the West Coast came the AER protocol that you've heard a lot about, the address event protocol. We used a lot of basically Kirchhoff's law to simplify computation. So additions became basically just summing of currents. Fan out became just essentially just putting voltages on wires and watching the wire changes. But on the West Coast, the notion was to try to also mimic the spiking nature of neural systems. We preferred not to do that. We preferred to do rate versions. But at the end, I think it's fair to say that the spikes approach to thinking about neurocomputation in silicon won out. And that's where now I'm a convert. So I'm actually a West Coastie at this point. So the neuromorphic engineering community basically grew out of these two groups in the US and maybe one group in Europe, Eric Vito's group. And this is a representation of what are the different groups around the world doing neuromorphic engineering now. Each one of these little knobs are actually multiple groups. Okay? And as you can see, there's one little knob in the middle of the Indian Ocean right there, and that would be me. I come from the Seychelles, and I've actually given a talk on neuromorphic engineering to people there. Not that anybody's doing neuromorphic engineering there, but I have tried to, sell it to the masses. And this is just a plug, just the fact that this NSF-sponsored and a number of DoD-sponsored workshop has probably been one of the most influential in growing these groups. And I suggest that, for those of you who haven't been to Telluride, please attend. And for those of you who have, we welcome you back. It's a beautiful place to spend 3 weeks in the summer, so please do come. All right, so why do we tackle vision? Well, we know that vision is basically quite well understood. There is a lot of problems that have been solved in vision such that, at least been tried, and we have benchmarkable results that if whatever we do in the neuromorphic domain, we want to be able to benchmark our results. If we can't benchmark our results, how do we know that we improve? Neuroscience of vision as well is essentially, there's a lot of it out there. We heard debates yesterday about whether there's too much of it, too little of it, not the right type. Nonetheless, we know that there's enough for us to go and look at what's out there and try to find ways to mimic the way that it's done in neuroscience. So vision also provides us a mechanism for us to move around the environment. So we care about structures. Excuse me, I'm moving a little too fast. We care about structure, about environment. We care about what it is that's in the environment, of course, moving around in the environment, interaction with the environment. So that basically brings us to this whole notion of vision is basically or robotics becomes a sensory motor integration task. We heard about that a lot yesterday. And if we can do that efficiently, of course, then we'll be able to interact with the environment in a more efficient way. So what are the different ways that computation for vision is being done today? So here's your classical computer vision chain of events, right? There's a camera up front. There's some kind of synchronized intensity map that comes from the image plane that then gets sent to a GPU, CPU, whatever to do processing, right? So the camera takes a snapshot in time and passes this information down. And I posit to you that that is exactly the wrong thing to do. So the entire, and I don't know if Alan is here, I don't see him, Alan Newell. The entire way that computer vision has been done until now is wrong. Okay? Because why is it wrong? Because we don't do this. We don't run and stop, take a picture, run and stop, take a picture, right? So things happen dynamically, continuously, and all of it, throughout time. So how can we build computation systems that are a little bit more like that? Well, we look at biological systems and we look at the spike trains that goes from the retina to cortex. That spike train, although there are some evidence of packetization, but nonetheless it ends up being essentially a full flow of information that goes continuously from the eye to the brain. So that's the kind of systems that we want to build in our vision systems, right? We want to have a camera that is somehow dynamic, that is continuous, that provides information as information that is relevant comes out, and provides these spike trains now that are then can be used. We can use processing elements such as Spinnaker, such as True North, the IFAT stuff that I worked on a lot in my career, and so on and so forth to do processing. So we are interested in these types of systems, right? These combinations of camera-like front ends, but information-like back ends, right? So information is going to be extracted at the front. So here are some examples of why this approach to vision works a little bit better. So what you're looking at here is on the left, your left, is a standard camera taking pictures of a pen being flipped into the air. And as you can see, once a pen gets to the top, you can hardly see it, right? Because of that snapshot effect, right? That essentially you're integrating while the pen is moving. Well, you're going to get motion blur, you're going to get all these kinds of things. In the middle is one of the type of cameras that I'm talking about, where you can see onsets and offsets events. So as a pixel, whoops, let me go back. Excuse me. As a pixel sees a change in intensity, that's when it reports its output. We have versions of this camera that can also give you an actual pixel value at the location where the change happened. So that gives us the mechanism for doing more than just looking for change. So the timing as well, in the sense of how fine timing resolution you can have between one pixel being output and the next being output, is also very, very fine. You don't have to wait for milliseconds for integration. You can do things in a microsecond time frame. Okay, so that's the type of things that we're trying to do. Why this is really cool? Well, let's take a look at this little video from this one. I will pass it over there in a moment. This video comes from the DVS group out of Zurich, but it also demonstrates the usefulness of this approach. Whoops, go over there. So what you're looking at there is a whoops, go away. Is a quadcopter that has one of these DVSs on board. Okay, and the DVS is being used basically for stabilization. So it's doing backflips, right? And the reason it can do that is because the speed at which these pixels are coming at you is fast enough for the control loop to react. If you take the standard camera shot, even if you speed it up to maybe hundreds of frames per second, you're still not going to be able to do that kind of fine control that you see over there. Okay, so this is the kind of things that ultimately having dynamic vision systems, having vision systems that output data, where every pixel is telling you what it wants. This is what we're basically hoping to get to. So we'll close that here for now and continue with where I am. So the alternative to Toby Delbruck's DVS is the ATIS of Christoph Posch, which is the one that I'm more partial to, because not only does it provide you your classical APS image, which is top left, it provides you a change image, which is on the right. It provides you a mechanism for knowing what were the values at the location of change. The values in the background, they behave a lot like the sustained cells in the retina. And the sustained cells in the retina, then you can apply reconstruction algorithm, basically like L1 norm reconstruction to get views of the background without even having to have all the pixels coming out of it. This particular little slide here is showing you what happened if you were going to output every pixel the way a standard camera puts out. This is the kind of data that you'd be putting out to reconstruct this scene, whereas with the ATIS, you only have to put out a little bit of data. From this frame over here, we can reconstruct the entire image that ends up looking exactly like this one over here. Okay, so this is really a powerful tool now that we can start thinking about what can we do with computation. Here's another example of just showing its dynamic range now, right? So you've got this bright spot on a standard conventional camera. You cannot see anything that's going on in the bright spot. But in on the ATIS system, you can definitely see the rotation of the camera. Hold up a second here. Close this. Okay. So you can see all the flipping around, and then he puts it in the dark. So the place is completely dark, where your conventional camera cannot see anything going on these types of image, event-based image sensors. You can still see what's going on in the complete darkness. So anyway, so I hope that I've convinced you that these types of image sensors are really effective in producing some types of data that is not easily accessible to standard camera systems. So now let's think about what computation you can do with it. So computing things like motion looks a lot like what we heard yesterday from Sebastian's talk, right? So we can create temporal delays that basically mimic your synaptic, mimic your dendrites. And then as events come out of this camera, these events are then projected forward to a layer that would accumulate the events. And you can add delays on these path such that, go to the next. Yeah. Okay. Such that as the bar moves along, you get this accumulation of events that ends up synchronizing on the time that they end up impinging on the neuron, right? So the moment you get that, then you get a spike at the neuron, right? If these coincidences did not happen at the same time at the neuron, you would not get an event that said this is the bar is moving with this particular velocity. If I want to make scenarios where the velocity changes, then I change the delays, similar to the Reich-Hard motion detectors that we heard talk about yesterday. And I also can change directions and so on and so forth. Okay? So with that, then we can create something like this, where what you're seeing is this pen is basically just moving as the motor is spinning it. On the bottom left, you see the speed every point along the black line, and you can see that, yeah, the tips is going faster than in the very center. Then as well as the direction, and you can see the color changing as the bar rotates because you're getting basically different direction along the pen. And this is all done with the notion of looking at time for computation. There's nothing about intensities, right? You can solve the aperture problem, which is a classic problem in vision, in motion, where essentially it's a barber pole problem, where you look at a barber pole, all you see is motion directly perpendicular to the gradient that defines an edge. Well, with this type of idea, you can combine spikes in such a way that it has basically a bigger field of view, and you can then solve the aperture problem in the weight space. Here's an example of an actual scene where the camera is looking at roads. It's got cars moving up and down. You've got this car moving diagonal over here. And if you watch the output, you can see that cars, in the first layer, it's very rough. There's some noise and some errors. And you've got the car that's moving up diagonally. By the time you get to the second layer and you start combining this information, solving the more aperture problem-like scenario, you get a lot cleaner measurement of motion. And again, all done in the temporal domain. Image stabilization is another interesting problem, is that, suppose I have a scenario where I have a scene that you have a camera that's looking down at the scene, and this camera is rotating and translating, looking over the scene. So if I wanted to see what the pixels of the camera is seeing, let me use this. This is a little bit, okay. This is what you would see, right? You would see basically the patch of the image that's seen by the camera as it moves along. Well, suppose I was able to take this image, I was able to generate an encoding that is probabilistic, that basically just does not encode the actual grayscale value, right? It encodes what is the probability of a particular pixel being a particular value. So if it's a certain, if it clears the probability, then it outputs a spike. If it doesn't, then it doesn't, right? So you get essentially a dense trace of spikes that corresponds to the addresses of each one of these pixels as they clear the threshold of the probability check. So from there, then I can apply all kinds of projections that allows me to basically do mathematics on the address space, and address space only, okay? So I can do projections where I can basically create convolutions, I can apply rotations, I can apply translations, I can apply recognitions, I can do all kinds of interesting manipulations of the data. But remember, the data here is not grayscale. That's really the key thing, right? The data is 1 bit per pixel, except the probability of that event from that pixel is what gets accumulated. And these events then gets accumulated in an integrated fire array, and then a decoder basically tries to predict what exactly did the encoder C. And here you can see an example now running a little bit slower, but the camera is moving, is rotating, tracing over Baltimore, and as it's doing so, this is what the snapshots that it's seeing, rotating, but in order to reconstruct a real-world representation of what it actually went over, you got to undo these rotations, undo these translations, and basically realign them, right? So if you know how the camera is moving, you can do all of that in address space, and that's really kind of what, to me, is the most interesting thing about computing with spikes, because all of that is nothing to do with intensity value, it's to do with the addresses and the occurrence of the statistics of the spikes themselves. Recognition is a slightly different problem. Classical computer vision, basically what you do is you take an image like this, you're going to apply all kinds of orientation filters that's going to tell you locally what are the distribution of edges that you see in a local area. So there are algorithms such as SIFT or HOG, which then creates a little histogram, basically every location, and then you're looking at the confluence of all the histograms in order to do recognition. That's basically the most effective way of doing convolution, doing recognition in a classical computer vision before deep learning and so on. Here, what we're basically going to do is again use the same timing idea that a filter that's constructed by combining the right places of where a spike came from with the right weights that converges on a particular neuron. You can build these filters automatically, or you can build them in parallel, multiple filters at the same time. Okay? So if I can do that, then I can construct, well, let me just, because of time, I'm just going to go a little bit faster. Oh, this is basically showing the case of, what happens if your edge is mapped to the filter, then of course all of these coincidences happen at the same time, your neuron fires. If on the other hand, your edge is not matched to the filter, then you end up essentially having this one event happening at the soma, then the next, and the next, and the next, and the next. And because of the confluence of time doesn't add up, you cannot basically see it. On the other hand, if you had an oblique filter that basically took the inputs from the right location in your image space, then you can get it to fire at the right time. And we construct all kinds of interesting filters of that sort. In most of these layered hierarchical mechanisms for doing feature selection, there's usually an operation which is similar to a max operation. It's a pooling operation. And in the classical HMax model that some of you may be familiar with, that max is actually a max, right? But here we're computing entirely in time, right? There's no level, there's no amplitudes to be considered, right? So how do you do a maximum determination? Well, you do it by looking at time to first spike, right? So if my filter is matched to my edgelet, then the way that my membrane potential ramps up, it will be such that the filter that matches right with the edge will fire first. Okay, so the moment that it fires, then you want to basically go and suppress everybody else. So you can build something that looks like this, which is essentially, lateral inhibition to construct these mechanisms for doing, for doing detection of which spike train actually matches the filter, is an indication that matches the filter first, right? And these types of interactions, of course, can be as wide or as big as you need it to be. So with that, then, you can construct, this is an image again coming from the ATIS. You can construct different onset and offset orientation maps. You can combine them together. And this is basically just showing the orientation of each piece of these lines on this cup. And it's consistent with what we would expect. And then from there, we can go and try to implement the entire hierarchy of HMax. Where we are trying to basically replicate this experiment where you could look at different sites and you could see bursts of neurons on these different sites that correspond to specific objects or specific inputs to the monkey. So here we are doing basically the same thing using Tommy Poggio's HMax methods, except looking at the statistics of the spikes at the very end, at the very top. We implement it in this way, And this is now showing the thing in action, right? So, you want to go to Las Vegas and you want to see, what is the order of the cards that are in the pack. Suppose I could tell you this, where I could go, and I can tell you every number or every pip that's in order, right? So that's the kind of thing that we would like to do. We would like to recognize the pip of the cards as you just do a flip on the order of essentially like 10, like milliseconds, and determine what you can tell. And we can now show you how it works. Similarly, in this case, in this case over here, what's going on is that you've got this ring where numbers are just zipping by, and you want to basically try to recognize numbers as it zips by on the order of, again, microseconds, right? So how can you do this? So the first thing that you must do as these numbers goes by, you must do basically a stabilization step, similar to what I showed earlier on. Then you've got to do orientation extraction, like I showed earlier on, and then at the end you do basically a pooling and you make a decision, right? Oops. So this is just showing it in action. So as the G is going by, the G basically gets stabilized in the center, and then the various maps tells me what the orientation of the different part of the G is. I get a more coarse map, and then from this coarse map, then I can do recognition and figure out what's going on. And that's true for pretty much all the different letters. And this is just showing kind of in the different layers. So the first layer, the second layer, which is kind of the complex layer, and then you have another layer that pulls information from the C1 layer and then ultimately to the C2 layer where you get the actual statistical distribution of spikes that corresponds to that particular letter. So how does it compare to others? Well, it does about, say about 97% accuracy. That number is a little bit difficult to say because you're talking about this continuous time here, right? So it's not like you present one image and say, well, did he do it? There's another image. No, you got to kind of integrate it over time and say how, as long as that pip or that number or that letter was recognizable over a certain period of time, how often did he tell you the right thing, right? This is a paper that actually that appeared in PAMI that used a similar kind of front end, but use a convolutional neural network to actually do the recognition. This is the work of Barnabe, Linus, Barranco. And as you can see, the approach that we're taking is a little bit different, and it does a little bit better. This paper, the H1st paper, should be appearing in PAMI anytime now. We're just waiting for it to come out. So you can get more details in terms of how it's all done. So, as I close this talk, here are the different scenarios that I want to articulate, right? So number one, right? So with traditional computer vision, you're dealing with frames. With real dynamic vision systems, you're dealing with continuous time. Okay? So how do you deal with these two, with these two disparate things? So you cannot apply similar ideas that you have in computer vision unless you bin, right? Which is basically what the integration time is. You take 33 milliseconds, you bin down, you get an image, and then you process it. Then you take the next 33 milliseconds, you bin down, you get a second image, and you process it. We don't like that. We think that's the way things used to be done, not done anymore. Of course, you get compression, the fact that you only output data where data is needed, where something new has happened. The notion of a frame rate is not relevant when you talk about dynamic systems of this type, because it all depends on whatever the resolution of the loop of when an event is detected to when that event is seen, right? And that can be, in this case, microseconds. It could be nanoseconds. In fact, some of the fastest cameras that we've built have, excuse me, see my presentation is telling me to get on with it. Some that we've built actually has like 40 nanoseconds loop time, okay, in order to get data out. There's no clocks. Anyway, processing is all done in time. And we can exploit coincidences. We can exploit the fact that when something changes in the scene, if they're correlated, they're going to change together, right? In fact, it allows you to think about stereo vision as well, right? Two cameras, when something moves in the scene, the event that where one camera provides its location and the next camera provides its location is going to be correlated. So the notion of disparity now is really easy to compute, right? Because you know just by the addresses what the disparity is. So it makes life a lot easier to compute. Anyway, so this is The folks that I work with, my student Jamal provided some of these slides. So Garrick, so Riyad and Christophe are from Paris at the University of Pierre and Marie Curie. Andreas Andreu, some of you may know, and Isidoros Doxis at BAE Systems, folks who make it happen. And again, remember to come to Telluride. We'll be happy to see you guys there. Thank you. Super clear, no questions. I like it. Or maybe I'm just preventing you guys from going to lunch.
No, well, that was an amazing talk. I guess people want to go to lunch, so I'm probably not happy to see me up here. But it was a great talk, but I don't know how to say it. It's so amazing to get the temporal resolution you do. Is that kind of dangerous because you're sort of in a non-physical, right? We don't see that temporal resolution. Is that distracting you maybe from thinking more about processing at the back end? I don't know. Is that a...
So, I mean, okay. So on the one hand, I mean, I don't know. Well, it's not distracting because from the perspective of it's the relationships of the spikes that we're seeing here. Getting a nasty echo. Is the relationship of the spikes that we're seeing that's down to that resolution, right? You're not going to get the same pixel outputting its output within 10 microseconds, right? It's one pixel and then the next to it to allow us to correlate these two values, okay? The only time that you're going to get the same pixel outputting the same thing like within 10 nanoseconds or 10 microseconds is if there's a really bright spot on that spot, right? Looking at the sun, maybe, you know. But that almost never happens, right? So it's a coincidence that is being exploited. So yes, so as I move, the relationship between 2 points on my image plane, you know, if they're related, if it's a rigid body moving across, should be instantaneous, right? Should be there. In the case of the ATIS type sensor, you get it. That's what your data tells you. But in the other case, you got to wait 30 milliseconds, and in 30 milliseconds, those 2 points could have moved apart, you know, by a long way. So in other words, usually you undersample fast things and you oversample slow things. In this case, you optimally sample exactly the right time that you need for the motion that's actually real, and that's really the key thing. That's the kind of the take-home message. Perfect sampling.
So a comment and a question. A lot of neuroscientists have argued that the brain encodes information, especially between receptive fields in correlations. But it seems to me that the reason that the brain adopts that strategy ultimately is because that strategy is represented in the environment. You know, when you move your eyes, edges set up correlations. And the fact that the brain ultimately applies that for other purposes, I think, is just a benefit of the fact that it's learned how to process from the environment. So that's the comment. The question is, in this sort of timing, our time to first spike regime, there is an ambiguity, right? The question is, are you firing now because the edges move past right now, or are you firing now because a less contrasty edge moved by a little earlier? And so the way that you disambiguate that, I assume, is because you have this suppression, right, that the slower spikes don't show up if they're not first.
Exactly, and also there are leaks, right? I mean, so if you take too long to show up, your influence gets diminished, right? So it is a leaky integrated fire type scenario, where you got to be in within a certain time, otherwise that temporal coincidence is not exploited.
Thank you. That excellent.
So absolutely. So in the sense that if you have a light that goes off and on, absolutely, that's going to be seen. Okay. So yeah, like the classical example is the old days. You take a optical mouse, you turn it upside down, you look at a fluorescent light, and your mouse went over the place, right? And there are ways to solve that, right? So you take care of that in the computation. You could basically, there's a classic paper by Van Satten and Sperling where he shows that if you combine temporal filters and spatial filters with the appropriate phases, you can completely eliminate flicker, because flicker does not translate. Flicker stays at the same path length as goes. And that's it, you can take care of it.
Just have one quick question also. So you use timing so exquisitely at the front end, but it's a little bit like you throw it away once you get into your back end. So is that your ultimate
I can speak two ways about that, right? So yes, there is some, it depends on what you're trying to do with it, right? So if I'm trying to do control, I'm not going to throw it away. I'm going to care about my exquisite timing, because the block that's receiving the events and making decisions are not going to be accumulating. They're going to basically take one event from that location, take the next time the second event comes, and from these two spikes make decisions, right, on that pixel or its neighborhood or something, right? But if I'm going to try to reconstruct a grayscale image, then yeah, then I take multiple events to create a firing on the output, right? And that, in that sense, you are right. You are back to an integration of events, right? However, if you have the timing and the weight set correctly, if the timing of the spikes does not come at the right time, shall we say, at the right coincidence, right, then you are going to end up having a scenario where the probabilities are not going to build up together, right? You're going to get basically these little lumps that are never going to cross threshold. So the timing is still in there. It's in there a little bit more implicitly, whereas if you're doing control, it's there explicitly. Yeah? Thank you.